This lesson is on Chapter 5, Section 1, Exponential and Logarithmic Functions. So open up your notebook, turn to page 362. Now you are going to have your books open and stay with me here throughout the course of this video because I will be making references back to book examples because I did not want to try to figure out how to type them or draw them somehow into the video lesson. So we are going to be going through some examples from the textbook together. First, in evaluating exponential functions, I'd like us to look through example number 1 in the text. It goes through the keystrokes for how to enter exponential values so that you can evaluate expressions that have variables as exponents. So taking a look on page 362 for example number 1. If they gave us the function f of x equals 2 to the x power and gave us a value of x being negative 3.1, okay, do you know how to take that and enter that into your graphing calculator or your calculator in general? Okay, so it shows you the keystrokes down there. You'd have the 2 and then the caret key and then whatever value they're having you put in for that exponent and so on. Okay, I think most of you know how to run the calculator, but run through those and punch a couple of them in to make sure. Checkpoint problem number 1 then. Use a calculator to evaluate f of x is equal to 8 to the negative x power at x equals square root of 2. All right, so when I punched this into the calculator, I kind of did those same keystrokes, an 8 and then a caret and then a negative square root of 2. And I came up with, hopefully you guys will too, 0.0528 when I did that. To graph exponential functions, you can build a table of values and use those to plot points. So look through examples 2 and 3 in the text. So again, I'm not going to do another one. For example number 2, they gave you two problems. They gave f of x is equal 2 to the x. Let's take a look at that one first. 2 to the x is the top row. 4 to the x is underneath it in that table. For both of the problems, they chose the x values negative 3, negative 2, negative 1, 0, 1, and 2 to plug in. So on example A, with f of x being 2 to the x power, if you put in negative 3 for the power of x, you'd have 2 to the negative 3 power, and that's 1 over 8. Then they went and put the negative 2 in for the power. 2 to the negative 2 power is 1 over 4, and so on and so on and so on. Okay? 4 to the x power, which is example B, they did the same thing. They took negative 3. So for the first one, it was 4 to the negative 3 power, which is 1 over 64. 4 to the negative 2 power would be the next box, 1 over 16, and so on and so on and so on. Okay? Down at the bottom of the page, example number 3, again, it's building that table of values. There's two examples again given to us. F of x equals 2 to the negative x and g of x equals 4 to the negative x. Go through those, punch the values through your calculator, and make sure that you end up seeing and getting the same values that you are seeing the textbook get in those tables. Okay, there are more checkpoint problems. I am not intending to go through them with you on the video, but they certainly can be used. You can just simply watch those extra videos on that ronlarson.com as well. All right, now there's a couple of things that I wanted to review with properties of exponents. One, you kind of have maybe in those examples 2 and 3 on the previous pages recognized or reviewed, whether you intended to or knew you were or not. If we have x to the negative 2 power, remember to get rid of a negative power, it takes a reciprocal effect. So if we have x to the negative 2, that can be rewritten as 1 over x to the second power. Okay, by bringing x to the negative 2 underneath the fraction bar, that negative on the power disappears. So another example of that, 3 to the negative 1 power is equal to 1 over 3. If we had 2 to the negative x power, again we can rewrite that as 1 over 2 to the positive x. Another way that this could be rewritten, and I think that you will see and recognize this kind of thing throughout some of our lessons, is we could rewrite that as 1/2 raised to the x power. Technically, the x power was not here on top, but it could be, because if you took 1 and raised it to any power, you're still going to get 1. That's why the rewrite of this over here works. Okay? 1 to the x power is the same as 1, and then the 2 to the x power still sits there, just written in a different form. Okay, so do you remember these properties of exponents? If not, that's probably something that you should come back to class with. Star it now, and we can do a little bit more discussion on that. Now, taking a closer look at elements of the graph y equals a to the x. All right, so we're going to be looking at these exponential functions, which y equals a to the x power is. The domain of a function like this. Okay, you can put any value in for x that you want. So the domain goes from negative infinity to positive infinity. Now the range is only going to go from 0 to infinity, because no matter what power we put in for x, we're not going to end up with a negative value. Even if you put a negative number in for x as a power, all it would turn into is maybe 1 over a to the second, or you're going to get some kind of a fraction value, but it's never going to dip below 0. So that's why our range would be stated from 0 to infinity. The y-intercept is 0, 1. And again, if you plugged 0 in for x, you would have a to the 0 power. Remember that a to the 0 power, or anything to the 0 power, is 1. So that's how this intercept comes about. Plugging 0 in for x will give us a y value of 1. This function is going to increase as the power of x gets higher, and I think you guys could pretty well figure that out. If we have a to the 1 power, then a squared, then a cubed, a to the 5th, or a to the 15th, it's going to increase, and it's going to increase fast. Horizontal asymptote is y equals 0, because these values are never going to go into the negative values. So y will always end up being a positive amount. There are no breaks in one of these exponential functions. It's going to be continuous. If you guys look on page 364, okay, you can see this curve y equals a to the x. Notice how they plotted the intercept, and then they followed from the negative x values and just hugged that asymptote of y equals 0. And then, as we know, when we get off into the first quadrant there, it's going to take off on a quick rise as those powers of x increase. Now let's take a look at y equals a to the negative x power. Again, you can stick any values in for x that you wish. So our domain again is going to range from negative infinity to positive infinity. The range, no matter again what gets placed into that power spot, you will not end up with a negative value. So our range again will bottom out at 0 and go to infinity, positive infinity. The y-intercept is again going to be 0, 1, because again, if you put 0 in the x spot, you're going to have a to the negative 0, which is still a to the 0 power. You will get 1 from that again. This is going to decrease. And if you think about looking at a to the negative x versus a to the positive x, if we were looking at an f of x here and we put a negative in front of the x part, remember from a few chapters back that that was a reflection. If we reflect that prior curve right here that we were looking at, it's going to go down. So it makes sense that this is going to be a decreasing function. Horizontal asymptote will again stay at y equals 0, and it again is going to be continuous. So with our intercept still here, we're going to be coming closer and closer to that y equals 0 line, but again never meeting it. But since it's a reflection on that y-axis, it's going to go up on this side. Notice how these two functions, this one and this one, are reflections of each other. Another thing that we're looking at in this section is working and finding out what exponential powers end up equaling. All right? There's a property called a one-to-one property. And it says that since all exponential functions either increase or decrease, they're going to pass a horizontal line test. That should sound familiar. We talked about the horizontal line test again earlier in the term. If a function passes the horizontal line test, they were one-to-one functions. So if we have this one-to-one property, we can use facts like you see down below. If, for example, we had a to the x power is equal to a to the y power, then those powers have to be equal to each other. Okay, so this is one of the properties that we can deduce from a one-to-one function. Take a look at checkpoint problem number 4 at the bottom of page 364. There are a couple more above it with the regular example 4s done out in the book. I did look to the checkpoint ones to give you a couple more examples rather than just going with the book. So if we look at letter A, we have 8 is equal to 2 raised to the 2x minus 1 power. All right, so the base of our exponential side is 2. So in order to evaluate, what we can do is we can rewrite our 8 so that it has the same base. So most all of you know that 8 is the same as 2 to the third power. 2 times 2 times 2 is 8. So replacing that or making that substitution, I'm now looking at this. Okay, so now we bring into play that one-to-one property that we had on the previous slide. The bases of these two exponents are both 2, which means then the powers have to be equal. So that means 3 has to equal whatever 2x minus 1 is. Solving my equation, I get a value of 2 for x from this problem. Letter B, if I have 1/3 raised to the negative x power, okay, that's the same as saying 1 to the negative x over 3 to the negative x. Okay, both of those numbers had that power outside the parenthesis, so it can be rewritten like I have. Now, to get rid of that negative in both of those exponents, you're going to use that reciprocal concept. So if I rewrite this with the 3 to the x power on top and 1 to the x underneath, I eliminate those negatives. Now, 1 to the x power is just 1. No matter what power you have there, you're going to get a value of 1. So now we're just going to consider that 3 to the x has to equal 27. So the first part of our problem has a base of 3 and a power of x. Let's rewrite 27, because we can, as some power of 3. 3 times 3 times 3 is 27. So now we have an expression on both sides that has a base of 3. If the bases are identical, the powers have to be the same. So the value of x in this problem ends up being 3. So those aren't so bad to play around with. Just remember, if you have one exponential piece, look at the base and what it is and see if you can't get the other side rewritten using that same base. All right, transformations of graphs of exponential functions. In this section, you will again recognize the relationships we have become familiar with when shifting functions. What caused left, right, up, and down shifts in the past are still going to apply to these exponential graphs that we're going to take a look at this chapter. So looking at letter A, I'm doing checkpoint problems at the bottom of page 365. I did all 3 of them. And if we take a look at g of x is equal to 4 raised to the x minus 2 power. All right, we kind of have an idea of what 4 to the x power is going to look like. Okay, what then would 4 to the x minus 2 look like? Well, remember from the past, if we subtracted a number from x in any of those other parent functions that we had, we ended up looking at that as a right shift of 2. That will again do the same thing to this, these exponential graphs. So again, that's going to indicate a right shift of 2. Letter B has 4 to the x power and then adds a 3 at the end of the function. Okay, what did that tail add or subtract end up doing for a shift? This was our vertical shifting. So this function is going to go up 3. from what the normal 4 to the x power would graph. Letter C has a couple of things going on. First of all, the negative x tells us that we have a reflection, and then the -3 at the end means we have a downshift. Okay, so on this one we have a reflection, and we are going to go down 3. All right, so most or all 3 of these in general come from the 4 to the x function. Then that other part that's tacked on, or those transformations that are done to it, are going to shift it the way that we have written here on our solutions. Okay, so it's kind of the same thing as when we were shifting those other functions. Okay, so you might have to brush back up on those shift rules. Now, the natural base E. I think you're going to recognize E from Algebra 2. Those of you who had pre-calc already, you certainly have worked with the natural base of E. E is an irrational number. Okay, it's a value of about 2.718281828 dot dot dot. It's a non-terminating, non-repeating decimal. That's what makes it irrational. So it does not have a definite value. It kind of just trails off in some random fashion. F of x equals e to the x is called the natural exponential function. If you look at your calculator right now, there is an e to the x button on your calculator that you're going to be using a lot. So take a couple seconds right now and identify or find where your e button is. If you can't find it, we're going to come back to class tomorrow so that we can get you located there and knowing how to use it. So the problem's in example number 6. I'm on page 366 right now. And again, all it's doing is guiding you through how to use your calculator to do these problems. So do them on your own, punch them through your calculator, and make sure that you end up with the same display on yours when you're done as what the book shows you for example number 6. Now, to graph a natural exponential function, you're going to be using your calculator to build a table of values and then plot the points. Take a look at example number 7 at the bottom of page 366. So this table, and we're only going to look at example number A here, I think, together since we're doing these sort of orally. The function they give us for A is f of x equals 2e to the 0.24x power. All right, so all they've done down below, and you're only looking at the f of x line. Ignore g of x. That's problem number B. Okay, so the f of x line is simply generated by plugging -3 in for the x in the function f of x. All right, so for that first one, you're going to have 2e to the 0.24 times -3 power. Okay, so see how you stick -3 in for the x value in that function. Hit enter, get your value, put it in the table. Clear it, now you're going to enter another x value in. Those values were chosen purely at random. You could pick other numbers if you want. If you want to have some bigger ones or some smaller ones yet, you sure can. But once you have those points, then you can graph. So look off to the side where you see figure 5.8, and they've done just that. All they've done is graph those points. So you can see -3 in the 0.974, -2, 1.238, and so on and so on and so on. Okay? So make sure, play with that function. Play with working 2e to the 0.24x power through your calculator and make sure that you're ending up with those same values that our textbook does. All right, next thing we're going to take a look at together. One exponential function that gets used a lot is the compound interest formula. I think you're going to recognize it because I believe you have used it before. The formula is a equals p times the quantity 1 plus r over n raised to the nt power. I've written here what each of those variables in that formula represents. R is the interest rate. Do not forget to turn your percent to a decimal. You have to turn your percent into a decimal. Time. T stands for the years. Okay, so adjust time if they give you months. Hopefully most of our problems that I've looked at so far do give us that time period in years. N is the number of periods per year. That will change based on whether or not you're going to calculate interest quarterly, which would be 4 times a year. Monthly would be 12 times a year. Weekly, I doubt that you would ever get compound interest weekly, but there are 52 weeks in a year if you should happen to need that information. P in the formula is your principal, or the original amount of your deposit. Okay, so that's the money part. If the number of compoundings increases without bound, okay, so it's kind of continually compounding interest, where it's maybe daily or something like that, the formula takes on a new form and it would require the use of that E key on your calculator. So a continuous compounding is going to be A equals P e to the RT. All right, so an example, checkpoint number 8. You're going to invest $6,000 at an annual rate of 4%. Find the balance after 7 years when the interest is compounded quarterly, monthly, and continuously. So if we're going to compound it quarterly first, let's take a look at that. So I have A is equal to P in 1 plus R over N raised to the NT. Now quarterly means you have 4 periods. Okay, so you break your year down into quarters. There's 4 of them. So my principal, 6,000. 1 plus, change your percent to a decimal. My number of periods is 4. And I'm going to raise that to the NT. Well, N is still 4. My time is 7 years. So I end up calculating 6,000 times 1 plus, this ends up being 0.01 to the 28th power. Remember, when you use your calculator, you need to do your exponent first, so that 1 plus 0.01 gives us 1.01 in the parenthesis. Do this first. Do 1.01 to the 28th power and then multiply by 6,000. And we end up earning this much money. Okay, so you punch that through your calculator and see if you match me. Letter B has us do the same thing except for monthly. So that's going to change it a tad bit. Instead of 1 plus 0.04 over 4, now we have it over 12. And we would also have then 12 times 7 as our power. So 6,000 and 1 plus, in this one, you know, it doesn't come out even, it's a repeater. You don't want to chop that off too soon, or it's going to definitely take out your answer. You won't be quite right. So when I punch this one into my calculator, inside the parenthesis I did the 0.04 divided by 12. I added on the 1 and hit enter, and I did not clear or write that. I just took that then and raised it to the 84th power, and then I multiplied by 6,000. And then that way I ended up with 7,935.08 dollars. Okay, so notice compounding it more often, compounding it monthly rather than quarterly, we're making more money. Okay, we've got about $8 more than we did the other way. So now make a guess as to what's going to happen if we compound it continuously for C. Right, so that was B, this was A, now let's do problem C. This is that other formula then. If it's continuous, we've got principal times e to the RT power. So we have 6,000 e to the 0.04 times 7. So we end up with 6,000 e to the 0.28 power. So again, do your power first. Punch in e to the 0.28 power on your calculator, multiply that by 6,000, and you end up getting 7938.78. Okay, So one of the main things I want to make sure you guys accomplish with this section is knowing how to use that particular key on your calculator. All right, so your assignment problems are going to come from 370 through 372. Last chapter, we kind of fell back on the amount of homework that we did and the amount of practice that we did. Hopefully you guys get back on the horse and do a little bit better job of getting brushed up and practiced.